This is me. My name is Eirik Bjorsnos. I work at Contega, Norwegian IT consultancy, and I'm based in Trondheim, Norway. And as most of you know, Norway is not the capital of Sweden. It's actually, they are separate countries. So in preparing for this talk, I've been watching most of, or maybe all of the videos I could find online from the Language Summit, and there seems to be a recurring theme, or at least a recurring slide, which is the legal slide. I could not afford a lawyer, so I had to make my own legal slide, and here it goes. The following is intended to make my mother proud. Unfortunately, she's not so happy with Java because every time she does internet banking, there's a new security update. OMG, there are some sharp brains in this room. I'm not nearly as smart as them. Will they see me for the fraud I am, or will I be able to fake it? Let's get this talk started, and we'll find out. But first, we need to update Java. And we're ready. So one of the things that I really like to do when I'm not in front of a computer screen is to hike and climb mountains. And sometimes when you look at the mountain for the first time from afar, it can really look really hard, or maybe even difficult, or maybe even impossible to get to the top. And but then you sort of take small steps, and eventually you reach the summit, and you can look down and be proud of your achievement. And for me, that's also the same in software. And for me, code coverage tools, it was 10 years ago, it was one of these difficult mountains to climb. And I really wanted to be able to stand on the top and know how it all worked. So in 2005, I created my first code coverage tool. It was called Ningdeck. It was very basic. I just proved that I could make it. And this progressed into a more feature-rich tool. I think one of the innovations of this tool was that I would display each line of each class as a vertical line, and each line of code as a pixel on that line, on that vertical line, and color them by not run, run, and recently run. So when you start your application, it would look something like this, where the coverage would be visualized. And if you reload your code, you will sort of see the code glowing in the dark as it's being used. Then came the next step, which was dogmatic MVC. Everybody has to create their own web framework. It used to be a very popular thing of the day. And it's called dogmatic MVC because it enforces that you have tests for your code, and that these tests have 100% test coverage, and that your tests actually find injected bugs. So here's a controller in dogmatic. You annotate it with a request handler. And in this case, we write hello world if you're from a remote address, and hello localhost if you're from 127.0.0.1. So let's say we run this from a remote IP. We should expect to get hello world. So let's try that. OK, dogmatic has intercepted our request, and it says, seriously, no tests. We're sorry, but dogmatic MVC just doesn't trust untested code. Please create a test class, add a test with annotation on your handler method. So let's do that. We add a test. OK, so now we should get hello world. No, we don't. Your test coverage is too low. Your coverage is 66%, and it needs to be 100%. And it shows us the line that is not covered. So we add a test for the localhost conditional. So now do we get hello world? No, we don't. We get this, which is saying that you're not asserting much in your tests, huh? We inserted some bugs in your class. Your tests did not catch these bugs. Please add some more assertions to your tests. And we add some assertions, and now, finally, we get our hello world. So the feedback I got from this after presenting it to a user group in Oslo was, please don't open source this tool. My manager will force me to use it, and my life will be miserable. I did not care. I open sourced it anyway. So I think an important lesson for me from developing this tool is that you can claim to have 100% test coverage, but it doesn't really mean anything until you know how well suited your tests are to uncovering actual bugs in your code. Having 100% test coverage usually just means you're exercising your code, you're not asserting. So the next step was revoc. And the new thing with this tool was that it's browser-based. It has an embedded web server, and it pushes your updated coverage data live over WebSocket to the browser application. And in this tool, I started focusing on performance. And when you focus on performance, this is what happens to your code. It gets really, really ugly, unreadable, unmaintainable. And I like to say that experimental optimizations, it's like CFOG covering your code. It's hard to see what's really going on. I think we have all experienced this from working on optimizations. So what do you do when you've coded yourself into a corner? Yes, that's Jason. I go to the Winter Tech Forum. It's a conference in Crested Butte, Colorado. Used to be called the Java Posse Roundup. And this is Bruce Eckel who's organizing this conference. It's an open space conference, so we have open space sessions in the morning, and in the afternoon we have usually snow-related activities. And on Wednesdays we have a hackathon day, and this is where you can suggest a project and you can gather a group of people and work on that project, and in the evening there is a demo and a presentation. So I suggested that we made a live code coverage engine from scratch in one day. And a few brave souls joined me. DJ, Dimitri, Todd, Jack, and Marshall, who's in the room. Marshall, there. And in one day we created Skybar, which is the next version of a code coverage tool. The name comes from someone said that we were setting the bar really high, and I thought in Crested Butte, the sky is really the limit. So that's Skybar. And 30 minutes before our demo, we got this from Hotspot. Is Vladimir Ivanov here? Yes, you're there? Yeah, I reported this bug. It turned out to be already a reported bug, but Vladimir was very helpful in analyzing it and helping us figure out what was going wrong. So thank you. Yeah, thank you for helping. Yeah, so for me it's been a kind of a progression of tools. NingDeck was about making it work. Dogmatic MVC was about making it fun. Revoc was about making it fast, and Skybar was about making it sane, making it maintainable, understandable, usable. So this talk is going to focus on Skybar and Revoc and the performance aspects of those tools. So the code coverage problem is actually pretty simple. You have some lines of code, and you want to know how many times has these lines, or branches, if you do branch coverage, how many times has each line been executed. Some tools sort of cheat, and they have a Boolean flag telling if the line has been executed or not. I want to count the actual number of times the line has been executed for reasons that we'll discuss later. So the design of Skybar is pretty simple. It's a Java agent that has a class file transformer which will instrument the user bytecode. And this instrumented code calls back with counting to a registry which is made available through the embedded web server, which pushes updated data as JSON over WebSocket to the browser, where there is a JavaScript-based application. So a simple way to create a code coverage tool is to look for line number instructions and then inject a method call which will count that line 18 in this case, as being executed. So that's pretty simple, but the interesting part for me is how do you make this run as fast as possible. And when you look at a simple method like this, it takes an integer and returns the absolute value. The naive and simple, straightforward approach would be to just inject for each line number instruction in the bytecode the bytecode needed to call a count method for that line. And this works well for simple methods. But if we have loops, and tight loops in particular, this can be very, very expensive. So here we are looping over integer max value number of times. So that should give us 4 billion invocations of the count method. And that's not good. So what we can do to improve this is to inject local variable counters for each line at the beginning of a method.
How often do you run out of 64K white codes?
I'm not covering that, but we can talk about that later. Yeah, you inject these counters, and then you use the INC bytecode to increment the count per line number. And then in the end, in this case, we have only 4 invocations of the count method, 1 per line. So this saves 4 billion invocations, which is pretty nice. So not all methods are really that simple. I don't know if you can see what's going on in this method. At line 11, there is an arithmetic exception, division by 0. So if we report at the end of this method, our return is really never reached. So we would lose the counts from line 9, 10, and 11. We would get no counting of that method. So to solve that and to make our truth correct, we need to wrap the whole method in a try finally block, or a try catch block in bytecode. And in the finally block, or the catch handler, we need to do reporting of all the lines. So if the method exits normally, it will exit through the instrumented return. Otherwise, it will be instrumented or counted through the finally block. However, many methods are, or most methods, I guess, don't throw exceptions. They're quite boring. They take some money from one account and they steal some of that money and make a profit, and then they update the account with a new amount, and maybe they do some auditing, and it's all pretty unexceptional. So in general, I think we can say that most code lines, when executed, will not cause an exception, and most code lines are not inside a loop. And I think it's safe to say that most code lines will run once and only once per method execution. I don't have proof of this, but it's just an assumption. So we can assume that all lines are run once. And this allows us to save counting, because we can count the method as being run, and then we can statically know which lines of code would be executed as part of running a normal execution of that method. And if there are exceptions to our assumptions about a line of code running only once, then we can report that line as, if it hasn't been executed, as running -1 time, which will cancel out the count from the method.
Excuse me, why did you pick that number 40?
I can explain that later, maybe tomorrow evening. Yeah. I'm not over 40, so I think that's the reason. So many methods are complex and dirty and ugly. They have loops, and they throw exceptions, and they have multiple return points, exit points. So I think the assumption that every line is run only once, it's a very weak assumption. It gives us a bit of performance, but it doesn't really give us good performance for complex methods. So then I got the idea, can we statically analyze a method to try to figure out at load time which lines must have run and which lines can't have run? And if we can avoid counting those lines, we can save a lot of counting. So in this method, these lines must have run exactly once when returning from line 20. And if returning from line 18, then line 20 cannot have been run, so it must have run 0 times. And then there's the lines that are inside the conditional or inside the loop. And who knows how many times these lines have been run. And those lines we need to report, but the other lines we know statically that they have been run once or 0 times. Yeah, this just repeats that same points, basically. We can skip reporting for statically known lines. So how can we implement this? I sent an email to the ASM library mailing list describing this problem and asking for input on possible solutions to this. And I got a response from Elliot Moss after some discussion, and he says something about dominators, or actually post dominators. And then he says the details would need a little bit of work. And this was May 23rd in 13, so a couple years ago. I looked on Wikipedia on the page on dominators, and I thought, And then 2 years later, I had this epiphany that I don't really need to understand this algorithm. I just need to be able to implement it in Java, and I'm done. So it worked. The only issue is that, as any sheep can tell, this algorithm is not cheap. It's quadratic to the number of nodes in the control graph. So I have not been using it. We have not been using it in Skybar. It's partially implemented in Revok, but it needs work before it can be practically used for large methods, because it will slow down the startup time of your program. Question?
You considered running it as part of a compilation instead of at startup time?
I have not considered doing that because I want to. Skybar is a Java agent, so it's sort of designed to.
It's just
But yeah,
it's taking one class file and writing it into another.
yeah, it's definitely the possible thing to do. Yeah, sure. Yeah, question?
Have you considered using ball and Laura's profiling?
Bingo.
Excuse me, I didn't hear that.
Efficient edge profiling.
I don't know what that is. So
So there are ways to annotate the control flow graph so that you don't have to derive all the points. You can salt them with places where you could derive everything else from.
Okay. So we need to talk later. Yeah. So so this part of the talk, we have discussed optimizing the instrumentation of counting. And now I'm going over to discussing implementing the counting itself. So the speed of the count registry. So that problem is basically for each line you need to look up the counters for that class. Then you need to look up the counter for the line. And when you have that, you need to add some number of executed lines to that count. And you need to write back the updated count. And of course, all of this needs to be done in a thread-safe manner. So I think the first approach that I tried was just having a map of maps where each using the class name or the source file name and pointing to a map of line number to number of executed execution times for that line, and then just wrap it in synchronized. And yeah, unsurprisingly, that's pretty slow. It's about as slow as Cobertura. If anybody has been using Cobertura, it's this slow. Yes, slow. So one way of improving on that is to not use map of maps, but to assign an index to each class as it's being loaded. So in this case, we can say that the abstract singleton proxy factory bean has index 0, and that line 9, which is the first line of that has code, gets index 0, and so forth. And this allows us to have, instead of a map of maps, we can have a two-dimensional int array, and we can replace map gets and puts with array load and array store instructions. And that improves things quite a bit. So a bonus trick related to that is that we can move the lookup of the class data to a generated class initializer. I think it's called in bytecode. And this has the additional benefit that you're also moving the synchronization on that array to class loading time. And we get to replace the array load with a getStatic field, which I think might be faster. I'm not really sure, but I guess there's people in this room who would know. It is, yeah. Okay, at this point, Java 7 came, and I read about Invoke Dynamic, and as a normal enterprise Java developer, I couldn't really find any use for it in my day-to-day job, so I really wanted to see if I could use it in a code coverage tool. And I thought about it for a while, and then it occurred to me that what these tools are doing, they're reaching out from the instrumented code, trying to get to the counters so that the counters can be updated. And that's expensive. So maybe we could use Invoke Dynamic to get the right counter at bootstrap time and speed things up that way. And it turned out to be really simple. So in the bootstrap method, or one of the bootstrap methods of Skybar, it looks like this. We are looking up the long adder for that line of code and that source file. And we look up the add method of long adder, and we bind that to the long adder and return a constant call site. And then we send in the source file name and the line number as bootstrap method arguments. So one of the interesting things of working on performance on code coverage tools has been concurrency and how to make this run fast on multiple threads. And I think I had two requirements. I want the tool to count correctly, so not lose counts. And I also want it to count fast, or as fast as possible. And if you look at it, adding a counter for each line of code in your program, it means that you're introducing mutable shared state on every line of your program, which is expensive. So the first approach was just to use synchronized to protect the updates. And that turned out to be slow, as mentioned. So the next natural step was using the lock-free atomic long class. And that works well until you start getting into contention. It's based on compare and swap, compare and set. So if there is high contention, you spend a lot of time retrying. So with Java 8 came long adder, which from my understanding, it has multiple cells, so it can sort of spread the updates over more memory. And this makes it slightly less atomically accurate, I guess, but it improves performance a lot under contention. So this is the fastest way I've been able to find until now, but I still think that there is room for performance improvement of code coverage tools besides using long adder, and I have some ideas for how that could be done. And yeah, let's revisit the requirement. Must count correctly. I think we can change this to must eventually count correctly. We don't really care if the counts come a few hundred milliseconds late, because our tool is not equipped to do anything with that kind of low latency information. So, but we need to be able to count correctly, like eventually. So one way of improving this is by using thread local memory. So this allows each thread to update or to keep counting in a buffer which is thread local. Which saves the volatile reads and writes to shared or volatile memory. So the threads, each thread can keep counting on their own, and at some kind of interval, they will decide to commit their counts into shared memory. And this needs to be done atomically using the long adder, as mentioned previously. So initially, when I looked into this, I got into a problem, which is that getting access in Java to thread local memory, it's really not all that efficient because it's thread local is implemented using a map, which is fast, but it's still a map, and it's not super fast, which I wanted. So I was looking into ways of trying to reduce the time needed to get access to a chunk of memory for the running thread.
Did you benchmark?
Yes, but all benchmarks are lies, and I don't want to lie to you, so I haven't brought any benchmarks here today.
Approximately the order of seconds.
I don't have numbers, but yeah, I could probably find some numbers for you, but not now. Yeah.
I know how to fix this.
You know how to fix it? Okay. So interesting. This is a nice conference, I must say. Yeah. Okay, so thread local map was too slow. I started digging into thread.java to see if I could find any state that I could exploit. And I found this. There's a private runnable target field, which keeps a reference to the runnable that was given to the constructor. And this field seems not to be used, at least by the JVM, after the thread has been started. So I was able to replace that with a runnable that was actually a buffer, the thread local buffer. So don't tell anyone that I did this. Let's keep it a secret. Yeah, question?
I mean, if you re-instrument the code, why not inject the field specifically for this instead of taking an existing one?
Exactly. You cannot insert field when you transfer like that. It's still the lyrics code.
Okay. I did not hear the question, I did not hear the answers, but it seemed like you were able to resolve it. So, good.
Well, you don't have to. You can do it when you boot rather than when you retransfer the file. So you would actually have to do it after when it's probably already built. With everything that is essentially done.
Okay, so we should write this down, or you need to come to me afterwards and tell me all about it. So a question here is knowing when to commit from thread local memory into shared memory. And that's turned out to be a bit of a tricky problem. You could measure time or use system nanotime, but that's just, in this context, that's just too expensive in itself. One trick that I tried was to have a thread that constantly writes to a volatile, that writes the current time to a volatile field. But that incurs the cost of a volatile read and write, or at least read, which was too expensive in this context. So what I ended up with was either keeping a count of how many times you have written, how many counts you have done, and use that as an approximation of time, or to keep track of your current stack depth and do the commits on certain stack depths. So this would typically be useful for let's say a servlet, where your request comes in, and when it ends, it exits up the stack, and you can commit once per request, basically.
Revisit the idea of writing to the volatile if you don't write too many times, because the writer thread is busy anyway, so the reader thread won't get a cache miss if you write if the change is like 10,000 nanoseconds already.
So you're talking about using the time or writing the time?
Yeah.
Yeah.
You said that your initial approach was if you write in separate thread
Yeah.
the volatile field. So if you don't write too many times, then the reading is cheap.
Okay. Yeah. Yeah. I guess we don't need to update time more than maybe every 100 milliseconds or something like that. So that could be an interesting thing to try out. In the end, for Skybar, I just figured this was all too fancy. We ended up using just the long adder. It could be something to revisit, but I don't want Skybar to turn into the complete mess that Revoc was. So let's try to keep it tidy. So a couple of things that have caused me grief. Yeah, stack map frames. I think I've spent quite a few evenings, nights, weekends trying to get my instrumented code right so that it would not blow up with verifier errors. It's very brittle, it's very hard to get right. It's hard to, the documentation is not really all that easy to digest, for me at least. But in the end, it's there, and we just need to deal with it. Another thing that I spent, I don't know how many days, but it was the counters in my tool in Revoc was counting the wrong line. And I've learned to kind of blame my own code first. So I started looking into my code, trying to debug, trying to analyze. I just could not figure out what was going wrong. And I was able finally to make a reduced test case. And it turned out it was a bug in Java-C. And I think this must have been there for many, many years. And the reduced test case is as simple as this. And the bug was that if you have a static inner class, you would,
Excuse me,
yeah.
no such thing as a static inner class. An inner class is non-static by definition. Static nested class.
Sorry.
Thank you.
Thank you. Yeah, such a nice place to be. Again, okay. Whatever happened here from the static whatever inner class something was that the Java-C here will generate a constructor for the class test, and that constructor had wrong line numbers. So the line number from the static class, empty, leaked over to the generated constructor of the outer class, which caused everything to fail spectacularly. And this is documented in JDK 8061778 bug report. It was fixed in no time, so thanks for that. Okay, forward-looking statements. Skybar, what's next? I think for now we have a speed that's sufficient that allows us to run the tool in a live environment. I think code coverage tools, they have traditionally been used as something you generate and show to your manager that you have some kind of test coverage, and it's all just not very useful. I think being able to use it in production on live running code opens up a new set of possibilities for new features. And I'm going to discuss a couple of them. And these are things that have not really been implemented yet, so I would like your feedback on these ideas. The first is what I call exploratory coverage. So let's say you have a certain state, a certain count, and you take a snapshot of that, a copy. And then you do some action. In this case, we have called the dewpost method. and we take a snapshot of our count state at that point of time. We call that B. Now what's interesting is to take the difference of B and A, and what we end up with then is really the answer to the question which lines of code were touched by triggering some action in your program. I think this can be very useful. You can find some button in your user interface, you can click a button, and the coverage tool will tell you which line were executed as a result of clicking that button. So this can be useful for, like, if you have a huge legacy code base and you don't really know where to start navigating it, it can maybe be helpful in exploring a code base. So building on this idea, there's something that I've called comparative coverage, which it's the same idea, but you run an action with a different set of parameters. So in this case, we're logging in, but we're conditionally enabling the remember me feature. So in the first case, we're not using remember me. In the second case, we are using remember me. And if we have the coverage, the differential coverage for each of these, we can compare them, and we can find the lines of code that differ when you are using the remember me feature. So you can sort of track the user interface into which lines of code implements this feature. Yeah, question?
Do you have any diagnostics that tell people if the code is likely dead, meaning it will not be executed under any circumstance?
You mean statically or at
Your
runtime?
analysis.
Yeah, that's actually the next slide, which is about detecting production dead code, which is code that, I mean, you can statically analyze a code base and find code that is not reachable. But sometimes it's more interesting to, or it gives an additional insight if you can watch your program running and find code that is actually not being used in production. Of course, it's hard to say because eventually it could be used. It could be some kind of yearly report that's run once a year, and you don't want to delete that. So, but it can give you insight into not only that the code is dead, but that the code is rarely used or used less frequently than you had imagined. Yeah.
So that's a much simpler problem than the one you're trying to solve.
Yes.
I mean, you only need to know whether it was executed once, right?
For dead code, yes, you need only once, but for knowing how many times an API function has been called,
Yeah, those are two different things.
yeah.
I mean, for dead code, I mean, one of the things we've thought of is sort of just hotspot knows whether you executed something or not. Just have hotspot spit it out, or you know, profile it, have it record once, and then retransform it and get rid of all the checks.
Yeah.
That kind of thing.
So I think that's an interesting thing because I'm not a JVM engineer. I'm doing consulting work. So I'm not intimately, I don't know the JVM. But if people have ideas for how this can be implemented better using tricks from the JVM, that's very interesting for me to learn about. And part of the reason I'm coming here for this conference, frankly. Okay, so yeah, I think this tool is partly a profiling tool, partly a debugging tool, code exploration tool, and a code quality tool. It's kind of hard to say what type of tool it really is. And if there are any more questions, I'm happy to answer them. Yeah.
First, about the stack map frame, you said it was a problem. Were you using ASM?
Yes.
Because ASM helps you, I mean, everybody probably who's done any kind of bytecode manipulation has encountered this, but ASM basically does have automatic frame map generation, and it does it for you, and it works.
It works sometimes,
Yeah.
most of the times, yeah.
Okay,
But
so
not
you
always, and that's not good enough. So
you have used that, but it does.
I tried using it, but it failed with exceptions on where it could not find a common. There's a method called getCommon superclass, which tries to find the common superclass of two.
In the current class loader, it tries to do that, yeah.
Yeah, yeah.
Which is
So if you have multiple class loaders, you're.
So you have to provide your own implementation for it. I know I did.
Yeah, I tried to do it, and then I decided I don't want to go there. So Skybar is not using. What's the feature of ASM where you enable this? Manage expand frames, something like that. Yeah, I turned that off, so now I'm hand coding all the stack map frames subtleties.
And that's how long? I mean, yeah, it was complicated.
When I just understood that I can't use getCommon superclass, it took just a couple of days for me to figure out how to do it without it. So, but I guess that's for my case, because I'm just wrapping code. I'm not introducing a lot of new. I'm not changing the stack much. Yeah.
One thing I want to say about the counting and long adder, what you were trying to do with French local is basically how long adder works. It's more complicated. It doesn't use volatile rights. It uses castes, but if there is contention, it like expand. It makes much better use of memory, and it basically does what it is that you want it to do. And it doesn't use volatile rights, it uses castes, but uncontended castes are cheaper than volatile rights, and that's what you want. You want to use long adder, and I wouldn't recommend trying anything else because it probably.
Yeah. Thank you.
And was written by Doug Lee.
And was written by Doug Lee.
And not by me.
The chances that you can do anything better.
Yeah, yeah.
That says nothing about you.
So I'll interject because I've had a version of a fast atomic counter like what Doug did there for a long time on the open source, and it does things a little bit differently than what Doug does, and you might try it. In particular, it might be cheaper for your particular use case.
And that's called.
High scaler.
It's the concurrent auto counter and high scale weapon.
Okay. Yeah.
You remove, so you modify the code and add counters in. And if I'm doing this in production code, that might be useful, but then it's like, okay, I'm done looking at this, now I want you to go remove everything you added. So I want it to go back to full speed.
Yeah.
Also do that.
That's a great feature. We haven't implemented it. I guess that could be solved by just triggering a retransform and then removing the transformer. Yeah.
It occurred to me that in the case where you're only interested in whether a line of code is executed, you could just have the bootstrap for the invoke dynamic bind itself to a no-op at that point.
Yeah.
Because
Yeah.
you only need to hit it once, and the bootstrap by definition is only hit once. So.
Yeah. I've also been looking into or thinking about using the guards in Invoke Dynamic to sort of maybe collect some runtime information about how this method is invoked, and then optimizing the instrumentation strategy based on runtime information.
Right. Yeah.
That could be done. Yeah. Yeah.
I don't know if it's the same. I'm going back to the ASM and whether it's stack mac frames for you. I had a problem when I was writing a micro instrumenter that it couldn't use getCommon superclass because getCommon superclass expected to be looking at the superclass, and the superclass wasn't loaded yet. And that was the issue we had. If you have that issue, I mean, if you search online, you can find like that will help you work around that. I have one in my open source ASM project. I don't know if that was the problem that you had or not.
Yeah. I don't want to deal with getCommon superclass for the rest of my life, so. But yeah. Okay. And we're done? Yeah. Thank you.